So good morning, everyone, or good afternoon, wherever you are. So the idea here is to show you what intent-based networking is, at least in short, and how it changes the way you could design your network, rather than looking at, should I do IBGP versus IBGP, or maybe OSPF, or should I use this number policy there? You need to start thinking differently. How to address my business needs, and design flow will allow you to express your business needs in a way that's going to be instantiated in networking you need, but at much higher level of abstraction. So the presentation is in three parts. One of them is kind of basic information about what IBN is and why are we doing it. Next one goes into more details about EVPN, and third one is tying Juniper and AOS together. So I've tried to show you what high-level intent on AOS results in terms of low-level configuration on Juniper switches. So with regards to questions, please ask question anytime. I'll try to address some of them in between parts because parts are very different in content and their intentions. So shoot it and we'll try to address them as we go. So why did we start working on IBM? Apstra has been around for 6 years, so problem is evident. And David Sheraton, our founder, has always been saying, networking is there, but management is not. So that's mostly the idea. And since foundation of networking, network automation, network management has been afterthought. And it's not for lack of trying. If you look at ITF efforts, YANC came up, OpenConfig got formed, but still we are spending a lot of time thinking of networking as a bunch of devices. Network is a distributed system and should be treated as such. It behaves like distributed system. It's no different than distributed system with databases or anything else. Networking is not special from this perspective. We are treating it specially, which is a problem here. So we've been trying for many, many years. And what you see on the picture is pretty much the response, right? I'm too busy configuring my stuff on CLI, and see you next year. So another important point here, in order to get complete and comprehensive view, you really need to understand your intended state as end state of distributed system. If you just look at configuration or, I don't know, ACLs, or just trying to prop some paths, you get partial view, which doesn't allow you to understand the state of the system. And this picture shows really well, like if you look at, I don't know, if you look at part of the elephant, you see spear, fan, rope, but definitely not whole elephant. So the idea is to see all of elements that allow you to say, my network is healthy, my network is unhealthy, something isn't working. From standardization perspective, there's great progress. We've got almost an RFC. It's going through last stages. It outlines number of fundamental building blocks intent-based system would build on top. The single source of truth is a database that holds the intended state for all of system. So it's not your configuration on device that source of truth. It's not. It's ephemeral from source of truth perspective. The role of source of truth is to provide one undeniable, unequivocal source of truth for intended state of your network. Intent-based analytics that are defined by context of your network and services you provide. So you don't ask 20,000 questions about what my network is doing. You only ask questions that are relevant to state of your network. And some points we are not going to cover here today, but you absolutely need to decouple policy definition from policy enforcement. And it's true for everything IBM does. Definition is high-level abstraction, and for all practical reasons, doesn't care about how and where you do it. There are some transformation functions within the system that allow you to produce configuration and place of enforcement that's most suitable for particular service. We are getting many questions in Apstra. Why did you start with data center? Why not one? Why not some other more esoteric places? We are lucky with progress of industry. Pretty much all networks today are form of leaf and spine networks. Russ talked extensively during last two classes about why are we doing this and particular properties of it. But practically, claw topologies are very regular, and they expand and mutate in very predictable ways. And this is very important in concept of IBM. We need to be able to reason about state of the network. And leaf spines are very regular. There are pretty much no exceptions. You know what your relationship between leaf to spine to super spine is. You know there are no parallel links because it breaks routing and connectivity. So it doesn't matter whether it's just 6 switches, as you see on your left, or F16 in Facebook. It behaves exactly the same way. So this is the reason. And if you look at Telka-1, that's what we see today in most cases, right? So it's going to take really a long time to try to standardize around what we do in the WAN. And there's a hope. The RFC 8453 provides really nice architecture to do so. There's a lot of work, mostly driven by 5G, by network slicing, some other stuff, but practically we are looking into it as the industry. We are making steps in the right direction, but the question is how long it's going to take and when. At Apstra, we have ambitions to be the intent layer for everything that's there in networking. Practically, it will take time, and we are progressing there. If you look at 5G specifically, the complexity is order of magnitude, because now you've got number of completely separate domains that traditionally never talk to each other. So you've got RAN, you've got core, you've got transport network in between. And if you look at specifications from 3GPP perspective, all of transport is just one small thing, cloudy, that's called transport network, right? But practically, in order to provision end-to-end service, you need to be able to understand state of all of them, and network slice is end-to-end at the end. If one of the parts in the chain isn't working, whole slice isn't. On positive side, we started to think about it. There are some initial ideas how we could use intent-based networking to provision network slices. The formal name in ATF is ITF, network slice. So this stuff will come inevitably because of complexity, because of variety of different elements. Probably one of the most important slides here, what IBM design principles are about. We are thinking about what we want, not how we are going to build it. The how is a job of intent-based networking system to figure out what to do, difference in semantics, difference in vendors, and place to place it. Think about ACL. In some cases, it's the best to place ACL as close to the host as possible. In another case, probably it's better to place it somewhere at, I don't know, internet exchange point, right? So it's the job of intent-based networking system to figure out, to resolve this high-level intent into particular configuration and place of enforcement. And there are many more details in draft, so we try to make it really comprehensive document in terms of what is IBM, difference between policy frameworks that have been produced by ATF and other standardization bodies, and how to think about it. Another very fundamental slide to IBM. You would have full workflow consists of 4 phases. So design, it's really intent consumption. You need to be able to consume users' intent in particular way that it's good enough to build something of it, right? There's a lot of talks about machine learning and natural language processing and whatnot. None of that is there yet. So what we do, we provide intuitive workflow that ask you the questions that are needed to build a service. And this is where intent modeling comes in, right? You could say, I want to build most crazy stuff. If it cannot be modeled and built as a network, system wouldn't allow you. So this is where modeling comes in. Instantiation. So at some point, you need to take your data model and bring it into real world, because there are inventories, there are devices, there are links. So this is where you apply your model to your existing stuff and see whether it can be done. Imagine you need a spine with 9600 gigs, but you only have spine with 4800 gigs. So here is the failure. And then validation. What's important here, validation is not afterthought. As you go through design phase, all validations are built because system knows what you're trying to do. It knows what's important to be able to unambiguously say system is healthy. So all the validations are built in process of your workflow, not afterthought. And if you want to change something, you're not going into deploy or build phase. You go back to design phase because system needs to understand what you're trying to do, model it accordingly, build all the validations accordingly. So in simple words, intent consumption, intent modeling, intent instantiation, and then continuous validation. Very, very high level view how an IBM looks like. For user convenience, to be able to interact with other people, you need to build something that people would comprehend, which is UI really, right? You go through particular elements of the system to configure it. However, we are in 2021. If your system is not API first, probably you did something wrong in design. So the RESTful layer of APIs should be able to provide you enough expressibility to configure your system completely without human being involved. So it's there. As we said before, single source of truth is the centralized storage of data, number of databases. So we're not going into details of internal implementation. It's a database that has full view of intended state of the network, and data is normalized. So if you are trying to render configuration for vendor Y versus vendor Z, firewall versus switch, single source of truth should be able to transform the data from high-level intent into something that could be configured or on vendor Y or vendor Z or firewall versus switch, right? So job of single source of truth normalizes data. And obviously, as we said, we always compare operational state of the network to expected or intended state. They should be the same if everything is working in sync. If they are not, it's job of the system to create an anomaly, to mitigate, to do something about it. And this is where whole continuous validation comes in. It's continuous validation of sync between operational and intended states. Just an example of how it looks in iOS. For example, your intent was to provision 5 different tenants. That's the level you operate in, right? So from configuration on device perspective, you should see 5 different VRFs or routing instances. By querying single source of truth, show me how many instances I should have on which devices. In iOS, we use graph database. What you see is a graph querying language. Here, I can easily derive there should be 5 devices, and I should have particular number of routing instances per device. I'll get this information from single source of truth. I'll query the network. Show me how many routing instances on every switch of type of leaf you have. I'll get the value. I'll do the comparison. So this is exactly what you see here. And this gives me ability to say, is everything working as expected? Is my operational state same as my intended state? Questions here? It was pretty much short introduction in what IBM should do with focus on what AOS is really doing. But so EVP and VXLAN. If we look at hierarchy of lanes in data.
You did get a question here. Benjamin was asking if the graph is part of the RFC.
No, absolutely not. It's an internal implementation, and there's a variety of graph databases available in the industry. Most well-known is probably Neo4j. In Apstra, we use our internally developed graph database. The modeling is internal, so the schema is internal to the system. What's described in RFC is the behavior of the system, not what the system is. Similarly, you might have 20 different BGP implementation. External behavior must be the same to comply. Internally, it's internal implementation. Back to hierarchy of planes in DC networking. So we've got management plane, which iOS takes care of. And then we've got overlay control plane, which is BGP VPN. We've got underlay, in this case, is BGP unicast and data plane. Focus of this discussion is BGP VPN. There are 5 basic route types needed for EVPN to work. There are more route types for multicast. Actually, there are few new route types coming every year as we progress with new use cases for VPN. Specifically, now we are going to talk about these 5, what they do and why are they there. So most basic route types needed for VPN to work are route type 2 that advertises MAC or MAC plus IP address, where IP address is optional. Route type 3 that advertises membership, mandatory for any switching to work because EVPN basically represents switch, right? For switch to work, you need to flood all unknown BAM traffic. So what we call unknown unicast, multicast, broadcast. Route type 3 allows us to figure out who are other members of the same EVI or bridge instance and flood traffic to them. This is how we build flooding domains. And route type 5 added later. It's not part of EVPN RFC. There's a separate document that is about to become RFC that defines what route type 5 is. Practically, it's to advertise IP prefixes without MAC addresses. We start with route type 2. It's meant to distribute information about MAC addresses. If you happen to have IP address, for example, host has ARPed, you will also have IP address. So let's try to tie together kind of high-level overview on ITF to what AWS is doing, and I'll draw on top to make it easier. So when you provision a virtual network on AWS, you could use either type VLAN or type VXLAN. For EVPN VXLAN, it's always going to be VXLAN. So the only information you really need to provision is unique name, because you want a name for it. It needs to be tied to particular VRF. You need to provision your VN in non-default VRF or non-default routing instance. It's mandatory on most vendors. We discussed it with some of Juniper folks. It's allowed on Juniper, but practically you would always want to have your VN created in non-default VRF. Then you provision VNI ID. VNI stands for Visual Network Identifier. This is the data plane component of EVPN VXLAN used to look up the packet when you receive it. Same way you would look up MPLS label in MPLS networks. So practically, this is the only piece of information we need you to provide. It could be auto-derived as well, but here, when you provide it, this is what's going to go into MPLS label 1 field. Let's remember, original RFC for EVPN describes EVPN in MPLS networks. So VNI goes into MPLS label 1. RT is auto-derived. It's going to become VNI ID column 1. Some other stuff is completely auto-populated by the system, right? Based on system interface, some other things. So practically, you see this very low-level picture and user interface that's very high level. But this is all you need to provision layer 2, or in Juniper terminology, bridge overlay networking. The end result, you are going to get VNI 10,000 configured. As we said, route targets are predictably set to VNI column 1. You'll also get mapping from definition of VN here. VLAN ID that's associated with it. If you have configured gateway or layer 3 component with associated RB interface and VNI associated with it. So you're pretty much done. For example, I also included AOS or Arista configuration here. So you see, while from configuration perspective, they are very different. They do exactly the same thing, and a job of intent-based networking system to figure out who is the vendor and what to do with configuration. Route type 5s are coming from either ARP entries received dynamically or configuration on Anycast gateways and such that being imported into EVPN. So from configuration perspective, what you see here, this is going to be your subnet on Anycast gateway and the virtual address of Anycast gateway and resulting configuration. You'll get an IRB instance with pre-configured or non-synchronized over BGP, as you might see in some other solutions, but statically configured. It will have same IP address and same MAC address on every switch that participates in this particular VM. The configuration in EOS is somewhat different, but again, it does exactly the same thing. So these values are going to be going into route type 5, and we'll see how they work. Depending on how IRB is implemented, you might see label 2 used or not completely. So security zone is a concept in AOS that is very similar to VRF and routing instance. It's a bit more extended, but for sake of this presentation, we will think of it as VRF. So when you configure VNI for it, it will go into MPLS label 2. In some case, in some other case, it's not. We are not going to go into details here, but there are 2 implementations of symmetrical RB. One where you use route type 2 with double labels, meaning your second label is fully instantiated with the IP address, route target associated with all the other data. In some other cases, the IP part of ARP will go into route type 5, and this is where route target is going to be associated with, so you can import and export those routes. Let's take a look. The resulting configuration is, we reviewed bridging configuration. This is a new piece that gets configured. This is your layer 3. It's your classical VRF or routing instance type VRF that has all the attributes that are needed for L3VNI to be created and propagated. So it gets its own route target. As we said, we use logic to create RT that is VNI column 1. So you see VNI is at 20,000 and route target 20,001. On EOS side or any other vendor, you would see this kind of configuration, which is very different, but the point here, your intent is getting correctly translated into different type of device or configuration. Type 3, as we said, is needed for flooding and membership. Not very exciting. What's important? Anything from route type 2 is copied here because you really need to import this route into same instance as your route type 2 goes to, because it's used for flooding. If you look at routing table, there's exactly what you would see. This is route type 3. And now route type 5. It has full set of different attributes to be able to use it without any other routing types. The only part that was missing in original definition was ability to encapsulate traffic such that the receiver would actually be able to look it up and say it's mine. This is done through RMAC extended community. It's exactly what it says it is. It's a router's MAC address or system MAC address of a device, encapsulated, not encapsulated, expressed as an extended community. So when receiver sends the route, what sender sends the route, receiver receives it and uses it then for inner encapsulation of MAC address. So when the receiver sends the traffic, it will use the router MAC address, inner MAC address. So receiver, when it looks it up, it can actually process it correctly and see that traffic is destined to him. Tying all pieces together, as we said, when we provision routing on VN, because it could be non-routed, could be what we call bridge overlay only, meaning there's no routing whatsoever, you only bridge. So this information will go into prefix. Virtual gateway IP address will go into prefix as well if needed. VNI will be derived from configuration of security zone, and your policies will also define what goes to be exported into EVPN. You could redistribute your connected routes, you could redistribute your static routes, you could redistribute BGP received from external router, right? So all of this will go and become route type 5 in the fabric. This is also how you provide external connectivity. Imagine you have an external router connected to you and it injects default route. Default route in routing instance will become route type 5 within fabric, and any device doing routing, when it doesn't know where to send traffic, it will look up default route. It will see that device that receives default route and transform into route type 5 is the next hop for it. Actually, it's NB interface. Send traffic to it. The receiving device will process it and send over unicast over the external router. And this is how route type 5 looks like. So very important point, why do we need both route type 2 and route type 5? Route type 2 IP address can only be host route /32. So by chance, this route is /32 because it's redistributed from loopback in the routing instance. But this route is /24. So if we wanted to do this with route type 2, we couldn't, because per definition, route type 2 is only meant for host routes. Similar output on EOS. Multi-homing. Route type 1 per ES is used for mass withdrawal. So if you have 20 million MAC addresses, you really don't want to receive 20 million withdrawals. You would like to be able to withdraw all of them on single type of signaling. RT1 per EVI is used for aliasing and load sharing. We'll go in bit details what it does, and RT4 for DF election. DF election is needed because we want only single member of ESI or ES to send broadcast multicast traffic toward the CE. In this case, DF election allows us to choose single forwarder while traffic is going to be flooded to everybody else. Remember route type 3, only designated forwarder is going to actually send it towards the destination. So some details here. Route type 1 per AS, you can always see that it has Ethernet tag set to max ETAG, so all Fs, it's easy to differentiate. 1 per EVI is set to anything but all Fs. So again, it's easy to see when you look at routes. What's interesting here, on Junos, for example, it's associated with special VNI ID, which is VNI 0. While 1 per EVI is associated with VNI that is set for this particular routing instance or EVI, and you would see this also in route type 2. So route type 4, as we said, it's used to choose designated forwarder. Important point here, you need route targets to be aligned, or import and export policies for route targets to be aligned between all participants in this particular ES. This is done by taking part of ESI, or 6 most significant bytes of it, and transforming them into community. So since we have configured ESI, we automatically generate route targets for it. So we make sure that everybody that participates in particular ES imports route type 4 and hence can run DF election. Very important point, there are a number of different ESI types. For all practical reasons, they have to match, because otherwise, depending on vendor and software release and whatnot, you might get inconsistent views. In most cases, we are using type 0, which is manually configured, meaning you could go and configure 9 octet ESI value. This is what AOS configures on Junos, and this is what every other vendor besides NXOS Cisco supports. Cisco generate type 3 for reason. Don't ask me. So if you use EOS, it will actually mediate between different types, and it's modeled internally in a way it can take type 3 transformed in type 0 and other way around. So again, you abstract vendor semantics here, and you could just express high-level intent. I want host to be multi-homed. That's all you need to know. And I'll show you how it looks like in terms of workflow. The end result of configuration is your ESI. In data centers, we always do all active. It makes really no sense in leaf-spine topology to do active standby. Stuff to make link aggregation group or aggregated Ethernet to work, and trunk down to the device saying, I want to see VLAN 10, 20, and 30. Route type 1s, as we said, we know that the attack will always be set to all Fs in a deeper ESI. It's going to be set to something different in 1 per EVI, and the route distinguisher will be different than here. Route type 4, the important point, your route target special here. It's so-called ES import target. And as you could see, the value of route target is auto-derived from ESI. This makes sure that there's automatic match between import and export policies on all devices that are member of same ES. So somewhat detailed overview of EVPN VXLAN and what it does on Juniper and Arista, and how iOS configure particular things, tying it to kind of low-level ITF details. Any questions here? Okay, let's continue to what Juniper and iOS do together in EVP and VXLAN. The emphasis here is we are not asking you, would you like IBGP versus eBGP, or maybe you like RIP, or maybe you like EIGRP, God forbid. We are asking you to provide your intentions, and it's a high-level overview of your business goals, really. So let's take a look how we reach and how we design with focus on business outcomes rather than nerd knobs or particular configurations. So what comes with iOS on top of Juniper this year is ERB, or Edge Routing Bridge and Overlay, meaning your services are always instantiated on leaves. In this particular case, we are talking about Anycast gateways. Till end of the year, the service interface is VLAN aware starting from next year, together with Juno starting to support routings of type MAC VRF on QFX. We'll also implement VLAN-based service interface. You've seen how we assign our Ds and our Ts. They're absolutely deterministic. There's nothing auto or magical about it. They're always going to be associated and generated in a way your VNIs are set, so you always know what it is. Full L2, L3 multi-tenancy, we'll go through it, and ESI multi-homing. So let's take a look what we do. When we provision a global bridge or global EVI, as we said, till end of the year, that's the only most supporting QFXs, we'll provision RD that is global for the switch. We'll provision RT that is specially used for route type 1. So remember, everybody in the network has to receive route type 1 to send traffic correctly towards ES. So this piece of configuration is hard-coded. It's unchangeable. And again, you don't need to know about any of these details. It's all done in background. Route targets for bridging information is set here. And as you could see, route target is always derived from the VNI value. So it's VNI column 1. From provisioning perspective, all configuration you've seen so far is this information, really. Your VNI ID and your subnet you would like to use for any Anycast gateway. That's all you need to provision. This can be also automated. So practically, you just need to give it a name and VNI and associate with non-default routing instance. The end result is, as we said, it's associated with non-default VRF. You've got VNI set. You can configure DHCP. Again, all of configuration is going to be auto-generated here. You say you want IPv4 connectivity or IPv6 connectivity. That's the only data you need to provide. The rest is auto-derived and done for you. So your intent here, I would like there to multi-tenancy. That's all you are saying. You're not choosing protocols. You're not choosing where you configure it. You only express your business logic and business intent. So the end result, you're going to use virtual network with VNI set to 30,000. You're going to have RB2 interface for Anycast gateway, which is here. And you're going to have under VPN options VNI 30,000 associated with route target 30,001. So that's fully working configuration for L2 multi-tenancy. For L3 multi-tenancy, you would use security zone concept. Actually, we've just renamed it into routing zone because it is what it is. It's a routing zone. So in new OS releases, you'll see different name. From configuration perspective, again, very simple. You are expressing business intent to have L3 multi-tenancy. And you give it a name, potentially VLAN ID you would like to use, and potentially VNI you would like to use. The rest of the policies, and as you could see, by default, you don't need to configure IP address or something that you need to go and look what it is. The expression is very high level. Do you want to see your L2H subnets, which is really your IRBs? Do you want to see loopbacks? You only need to click here. System will take care. So the graph query is going to be, show me all devices of type leaf, show me all routing instances, show me all interfaces that are loopback. So in this case, it's a single routing instance, but practically I'm trying to show you how graph database simplifies this. You've got all the relationships you need to walk the graph and figure out what needs to be configured here. So the end result is going to be here, really an expert policy that matches all of these fields, right? May you need some extra stuff that's not modeled. We still allow you to do so, but here you can put any IP address, and if you break it, it's your problem because you really shouldn't be doing this, right? We allow to do this because our customers have asked for it, but practically you would really like to use intent-driven workflow rather than specifying nerd knobs. So same goes for all the policies. As we said, route targets are auto-generated, both import and export route policies. May you need some additional import and export policies for DCI, for example, you can configure additional ones. So they will be imported and exported in addition to system-generated ones. The end result of this very, very simple intuitive workflow is this configuration, right? We would configure routing instance with all the information needed, all the export policies you have expressed, and may you have an external router. You would also have an external router here. So all the information here is auto-derived. If you remember, you haven't configured which interfaces need to be there. You haven't configured route distinguisher, route targets. So information that need to be hard-coded is hard-coded. Information that need to be auto-derived, for example, route target here is a function of VNI column 1, will be auto-derived in runtime. ESI multi-homing, perceived as complex. When you do it with AOS, your only intention is to say, I would like this particular server to be dual homed. I want resiliency. And this is really business intent because connecting your server twice is more expensive. It uses one more cable, one more port. But this is all you need to say. You only need to choose the server you would like to dual home, and you would need to use, or you would need to decide to which ports physically it is connected. That's all you need. This is the configuration that's going to be generated. So as we said, we use ESI type 1, where generation of ESI is done by AOS. We copy part of ESI into LSTP keys. So you can see LSTP here. And system ID is derived from part of ESI. In multi-vendor scenario, type 0 used on Juno could be transformed in type 3 used in XAS and Cumulus. All of this is validated, because remember, you express your intent with regards to multi-homing. But internally, we know exactly how many route type 1s, route type 4s need to be generated. And it's all going to be validated after you have configured and committed your configuration. So you see the routes. This is pretty much what we would do internally to validate that intended state is in sync with operational. Last piece is DCI. So again, DCI, all in all, is complicated in terms of provisioning. What we are going to describe here is over-the-top DCI, which is similar to interest option C, where VPN, AFIS are exchanged between devices in data centers, and unicast need to be exchanged in order to be able to resolve next hop. So in MPLS case, it would need to be labeled next hop. In VXLAN case, it doesn't need to. It's just IP address that is your VTIP uses, because this is going to be your next hop in BGP update. Important property here, as you start advertising your EVPN routes here, next hop must be unchanged. If you change next hop, you lose the originator of the route. The way we resolve next hop is over information we get from here. So it's a combination of these two. So I would like to show you how this would look on EOS. There's very simple workflow that's called remote VPN gateway. We'll go in details through it, but practically you don't need to configure a lot of different things. You just go through this very simple intent consumption phase, configure it on both sides, and you're pretty much done. So let's take a look at how it looks like. Workflow is, you name it again. You provision IP address of your peer, it's ASN, TTL, you would need password if needed, some BGP parameters such as keep alive and hold timer. And then, since in iOS designs, every device is participating within EVPN, you could choose devices you would like to instantiate your EVPN gateway on. Since it's a logical function, in this case, you see graph query. Show me all devices of role leaf. If I would have said spine, I would only seen spines. If I would have said all, I would have seen all the devices. So since I'm looking for leaves only here, it shows me all the devices of role leaf. By simple click, I could say I want BGP EVPN gateway to be configured on leaf 1, or maybe leaf 2, or maybe all 4 of them. They will all share characteristics provision here. So in other words, you will get, if I choose all of them, 4 separate EVPN sessions to this IP address. This is the configuration that would be generated. So remember, we said we must not change next hop on generation or when we send EVPN routes to remote. Some policies, TTL we configured, hold time we configured, and password we configured. So this is reasonably complex configuration. It's auto-generated as part of this workflow. Internally, we are, actually it's in process, but we are using a community tagging framework to be able to use distributed information. So metadata attached to BGP routes known as community to verify routes. So in this case, if we would like to see all routes we've received from EVPN gateway, remote EVPN gateway, it's associated with community. It's actually much longer, but this is just to show you an example here. And if we need to validate, when we need to validate, we just need to mention this community. We get all the routes that we received from. Yeah.
Somebody just asked if AOS supports ESI multi-homing or only ESI dual homing.
As of today, we modeled ESI as a REC, meaning it has 2 switches in it. We are looking into extending it.
So it's only dual homing right now. Yeah.
Yes, exactly. We are looking into extending it. From modeling perspective, nothing prevents us from to workflow would be somewhat different. And yeah, from use case perspective, in most cases, people are asking for dual homing because otherwise you would need to have horizontal cabling between racks, which is not common. But practically nothing prevents us of doing this. It's modeled in a way, it's independent of number of switches ESI is connected to. So to summarize, and again, this is the most important point here, intent-based networking is about what you are trying to achieve, not how to build it. It's job of intent-based networking system to figure out how. That's it for today. If you feel you need to ask something personally, please do. You can find me on LinkedIn or Twitter. And starting from today, my email address is jtensura@juniper.net. Thank you for your attention and hope to see you soon.